Hello friends, we were trying to understand semiconductors in depth through our previous videos. In the last video, we were trying to summarize the concepts and theories that we were learning into relations and equations. In today's video, we will see yet another equation that will help us understand more about semiconductor devices. In our previous video, we had seen continuity equation. Why we are interested in continuity equation is that it gives the rate of carrier buildup. If we could understand the rate of carrier buildup, we could easily find the current in the semiconductor. So whatever we are doing, we are trying to understand the current in the semiconductor. Moving on, another equation of our interest is known as the Poisson equation. Poisson's equation correlates the electrostatic potential phi to a given charge distribution rho. This can be derived by using a relation between electric displacement vector and electric field vector. It is related with the permittivity epsilon, or in other words, the electric displacement vector is equal to epsilon times permittivity times the electric field vector E bar. As you all know, permittivity is a characteristic of the material. Permittivity of the material is given by the product of relative permittivity and permittivity of vacuum, which is a characteristic that we can obtain related to any material. Before we move on to write a Poisson's equation or derive a Poisson's equation, we need to know about Maxwell's equation. Though we are not going to explain this equation since it is not in the scope of our study, I would recommend you to just do a search on Maxwell's equation and try to understand little bit about Maxwell's equation. Though we are having 4 of them, in our discussion we will be using only the first equation, which is also known as the Gauss law, in order to find the Poisson's equation. The Gauss law is a correlation between electric field due to the presence of electric charge. So del, which is a del operator, del dot D, which is the displacement vector, is equal to rho, the charge density. Also we know another relation, or you should know another relation regarding electric field, which can be represented as a gradient field of scalar potential field. Scalar potential field is given by phi. When we do the del operator on a scalar, we get the gradient. So the electric field is given by minus del phi. Now these two equations can be used into the relation that we had seen in the previous slide of displacement vector connected to permittivity and electric field vector. Now by substituting the equations 2 and 3 in 1, we can get a relation del dot epsilon del phi. So in place of d bar in the first equation, we are writing epsilon e bar, and in place of e bar we are writing del phi. That is the change that we are making, so that the final result which we require is obtained as del dot del phi is equal to minus rho by epsilon. Now, what is this rho? The space charge density. It is a combination of whatever carriers or charges that contribute to the charge density, which includes the hole concentration P, electron concentration N, and also C, the concentration of additional charges, typically fixed charges, that we had discussed earlier, but it was not written down as such. To elaborate on this, another additional charges are those charges like charge impurities of donors, Nd, charge impurities of acceptors, Na, which are in existence because they have donated their electrons. The donors have donated their electrons as free electrons. So it itself becomes a charged impurity. Similarly, the acceptor impurity have accepted an electron. So it has become a charged impurity, acceptor impurity. Similar to that, there are other additional charges like the trapped holes rho p and trapped electrons rho n. What is a trapped carrier? As you know, while we discuss in the energy band diagram, we had fixed conduction band, valence band, and in between we have told of Fermi level. But within the forbidden gap, which is between conduction band and valence band, we had assumed that there are no energy states. But in reality, there can be some states where the electrons from the conduction band or holes from the valence band can move into and get trapped. Those are additional charges known as trapped holes and trapped electrons. So, in a nutshell, the space charge density rho comprises of all holes, electrons, and the additional charges like charged donor impurity, charged acceptor impurity, trapped holes, and trapped electrons. With this knowledge, we could finally write down what the Poisson's equation is. We have already written del dot del phi is equal to minus rho by epsilon. In place of rho, we are writing Q into P minus N plus Nd minus Na plus rho P minus rho N, which is the commonly used Poisson's equation. And why we need this Poisson's equation is that to understand the current flow in the semiconductor, which is being doped by impurities. As we are moving to the next module where we will be discussing about PN junction, these factors, the knowledge of these factors will help us to understand the current in a PN junction. So this Poisson's equation becomes a basis of our discussion, our future discussion in module 3. Now we will discuss about a different concept. We have already seen what a Quasi Fermi level is. Quasi Fermi level was those Fermi level which get introduced when you are doping the semiconductor with impurities. Initially in our discussion we were just considering one Fermi level, but if we are doping with n-type impurities, we will get a Quasi Fermi level closer to the conduction band, and the p-type impurities will form a Quasi Fermi level near to the valence band. We had seen that earlier. And while we were discussing about drift and diffusion current, we were not concerned about this Quasi Fermi level, because we were just considering the equilibrium condition where we are having one Fermi level EF. But it have a relevance in our discussion in drift and diffusion. Any combination of drift and diffusion implies a gradient in the steady state Quasi Fermi level. If you remember the current equation, the current density, which is a combination of drift and diffusion, that will be the basis of our discussion here. We just consider the electron density, and in that we could substitute dn of x by dx with the Quasi Fermi level equation. You are deriving the expression that we had for Quasi Fermi level in our previous discussions, which will be equal to n of x by kt dfn. Fn is the Quasi Fermi level of n-type nearer to the conduction band, dfn by dx minus dei by dx. Now if we substitute this value in the previous equation, in place of dn of x by dx, we will get Jn of x is equal to q mu n of x e of x plus mu n of x d by dx of fn minus d by dx of ei. We are making use of the Einstein relation to make the equation in this shape. And we could approximate this dei of x to qe of x, so that the remaining thing will be Jn of x is equal to mu n of x dfn by dx. This shows that the current density, when considering drift, diffusion and recombination, will be related to the gradient of Quasi Fermi level d by dx of fn. So this relation shows us that we could directly relate the gradient of Quasi Fermi level to the current density. So our discussion on module 2, which was mainly on the carriers of semiconductor, ends with this discussion. Though we have another topic which is an extension topic to this discussion, which is the Hall effect, which we will see in our next video. And we will also have a tutorial on whatever that we had seen in module 2, which will help you to understand more about the carriers, current in a semiconductor. Thank you.